So without further ado, we'll get going into the program tonight. Again, if you guys have any questions, just let me know. I appreciate you joining me. This is the second to last installment of our winter series, if you will. So I just put up the whatchamacallit, the PowerPoint. And again, we're not going to hit every slide in depth, but there's definitely some parts of it that I will hit hard. And tonight I'm definitely going to hit some of the more general things. Whereas when I go to a department and do a class, there are some things in here that I'll take out, some things that I'll add in to fit specifically to the cameras that the department uses. Obviously, tonight we have a wide range of users, so we'll kind of do it that way. So these are, when we do the whole class, this is kind of the entire class. We'll go through the objectives, how it all works, some of the background details, the electronics of it, and then we go through calls. So smells and bells, approaching the building, meaning you're either doing your 360 or you're the officer approaching the building, at the front door. So where I kind of think of that is if you're the officer and you've got a nozzle man, while he's testing his stream or while he's making sure that, he's got water, or while you guys are waiting for water, the officer can and should, right at the front door, take a good look of what's going on inside with the camera. Then fire attack, so how we use it for fire attack, searches, how we use it for searches, a little bit about overhaul. We'll definitely touch on some of the limitations of thermal imaging cameras. And then, like I said, the NFPA 1801. It's actually a new standard now. I 2020 or 2019, whatever it officially, I think it's 2020, it officially came out. So there's a few changes in there that we'll discuss as well. Okay. So how it all works. So basically a thermal imaging camera, you have, obviously we have eyes, we can see, but what we see is a part of the spectrum. And when you have, a fire or smoke, there are those carbon particles that are blocking our vision. Okay. But the infrared wavelengths can actually get through the smoke. The carbon molecules does not block the infrared wavelengths, and that's what the thermal imaging camera is able to see. So it's not that the camera can see through smoke and it can see what's going on the other side. It's just that the camera can pick up the infrared wavelengths, the infrared energy that our vision cannot see. Okay. So this is just like a blown up diagram, kind of. Again, you have the infrared energy or infrared radiation that comes here. You've got the lens that lets it through, and that's usually a replaceable of some level. Then the lens in there, there's a shutter that calibrates, and then the secret box in here that gives us a regular LCD screen on there. So again, we're not going to get into it any more than that. Suffice to say, the important thing is that the camera is not seeing what we can't see. It's just seeing a different wavelength. It's seeing the infrared energy. This is probably, again, there's a few things tonight that are really important, aspects to take away. And one of them is what provides a good image. And so it's not high heat that provides a good image. It's not low heat that provides a good image that we can see. It's the contrast of temperatures. So I could put 5 objects next to each other that all have the same temperature, whether that be 0 degrees, 50 degrees, or 1,000 degrees, and they may not show up because they're all the same temperature. Whereas if you put those 5 objects at different temperatures, regardless of what those temperatures are, that's what's going to give you a good image. And so a couple examples I have here, we have just a blank wall. And because there's no difference of temperatures anywhere in that wall, you just get a featureless image. Here we have a room in a winter day, winter night, with a fire and a fireplace here. And you can see that there's, a hotter object here. And because all of these objects in the picture are different temperatures, that's what's giving us a good viewable image. If these were all the same temperature, it wouldn't matter if it was 500 degrees or 0 degrees, we would not get a good image in there. And then here inside of a burn building, again, you have different objects at different temperatures. You have a hose line here that's cold. You have a hose line here that's a little bit warmer. You have firefighters here that have obviously absorbed some of the heat of the building. And so those differences in temperature is what's giving us a good viewable image. And so as we go on tonight and as you use cameras in the future, that needs to be the primary focus of getting yourself a good image, is knowing that it only is going to provide a good image if there's a contrast of temperatures. All right. So as you said, the camera does not see heat specifically. It does not see fire specifically. It does not see people specifically. It's just giving us a viewable image based on the differentiation in temperatures. Okay. And the electromagnetic spectrum is what this is based, what this is all based off of. Kind of had a brain fart a couple minutes ago. I couldn't get those words out. But this is where the infrared energy is. So this is that electromagnetic spectrum. I know I sat through middle school science thinking I would never have to see this again. Certainly I didn't pay attention when I listened to it the first time. And you can see that this is the area that we see. And there's a lot of, terms up here that you probably hear on a fairly regular basis: AM, FM, long radio waves, microwaves. And so as you can see, this is where the IR, infrared energy, is. It's right next to where our viewable spectrum is, but it is different. So again, the camera is not just seeing through smoke; it's seeing a different energy that's coming through that smoke that we cannot see. Okay. So in order to know kind of how things show up on cameras, we got to talk about what is producing, or where do we get that infrared energy from. And so there's a couple types of emitters. And what an emitter is it's something that creates that infrared energy. And there's obviously going to be things that create more infrared energy or less infrared energy. And that may affect how it shows up on the camera. So an active emitter is something that's continuously producing infrared energy. So that could be us. It could be a heater, a overheated ballast that still has power to it and is continually producing heat, an outlet, wiring that is heating up and still has power to it. And so it's continually producing heat. And these items generally are more readily visible on the thermal imaging camera, because if you think about coming into a room, the majority of items in the room are not producing infrared energy, constantly. A table is not going to produce infrared energy. A wall is not going to produce infrared energy. Those are just states of matter. And so anything that is producing infrared energy next to something that isn't is generally going to be hotter, produce more energy, and therefore be more visible on the thermal imaging camera. I just mentioned a couple of these items: a couch, a desk. These would be a passive emitter. So it's something that does not actively produce infrared energy itself, but it is something that can show up on the thermal imaging camera if it has a different temperature. And some of those ways that it would have a different temperature would be if it was exposed to an active emitter. So I'm sitting in a chair right now. If I get out of this chair, obviously the chair is going to be a little bit warmer because I've been sitting in it for a little while. So although the chair itself is not putting out, infrared energy, and it has become a passive emitter once I stand up from it, it's still going to have a heat signature because I was sitting in it. So that's kind of what a passive emitter is. And there's many reasons that it could or could not show on the thermal imaging camera. All right. So this is another example of a passive emitter. So this would be a car seat, a driver's seat, where we had someone sitting in it and then they got out. So there's that heat signature, but then a few minutes later, there's no heat signature left. So again, the difference, the object absorbed the heat, but at some point it's going to let that heat go. And so that's an important, this is just an example, but all the time we're going to, car accidents, and someone says, let's grab the camera and see if someone was sitting in the car, see if there was a heat signature. And that's absolutely a heads up move. But it can't be the only thing that we look for, because on a cold night, obviously the seat's not going to hold on to the heat as long as it would on a hot night. Okay. And then a direct emitter would be a high energy infrared source. So that would obviously be things like fire or sun. that we run into, which is probably what most of us brought cameras for. So the other important part to go along with the emitter kind of discussion would be emissivity. And this is the rate at which an object reflects or absorbs that infrared energy. And so this is important. This deals more with those passive emitters, because the emissivity rate is going to determine how much of that infrared energy the object either absorbs or reflects. And that's important for a few reasons. So a zero emissivity rate is something that 100% or almost 100% reflects the heat, and that would be like silver or something really shiny. And then one would be like a black body that absorbs all that heat. A block of ice is a very good example of that. So again, something that reflects the infrared energy is not only going to reflect the energy itself, but with the thermal imaging camera, many times it will show up as a mirror-like image, which, as you can imagine, in a large-scale environment, could certainly fool the thermal imaging camera user. Okay, so again, different objects are gonna absorb differently, reflect differently. So this is, again, no one should be writing this down or anything, but this is a good example, kind of list of things that absorb and reflect the infrared energy. And so as we crawl around and as we play at our next thermal imaging camera drill, look at some of the more things. Everyone has diamond plate on their rigs, so look at that. That's going to reflect the energy, and you'll see more of a mirror-like image. Look at where ice, take a block of ice and see how that absorbs all of the energy. And wood, obviously we use cameras on wood all the time to see how it absorbs energy. And so, these numbers are just kind of a baseline so that you kind of know what materials out there will reflect and absorb the energy. So more importantly, what this is going to do is if I put all of these objects next to each other in a room and I heat that room up, the different emissivity values is what's going to give me a good viewable image, because all of these objects absorb or reflect infrared energy at different rates. They will heat up at different rates. They will be at different temperatures, and that's what will give us our good viewable image, because we will have a contrast of temperatures. So right there, as boring as this definition might be, this is what gives us a viewable image on our thermal imaging cameras, specifically of passive emitters. So the other thing we'll address, and probably we're going to spend some time on this early stuff, because I think this is kind of the backbone of thermal imaging camera, and frankly, it's a lot of the stuff that I don't think is addressed out there as much. So what I like to do is just kind of explain pixels and resolution quick, because we all have TVs, and so we've all heard these numbers. And when it comes down to marketing, this is where a lot of manufacturers will sometimes sell you a bill of goods in terms of how good the camera is by quoting the pixels of the screen. And so there are two generally pixels that are actually on a camera, one being the screen itself, and then one being the sensor that actually takes in that infrared energy. So a pixel is basically just a single dot in the display, and together they make up the viewable image that you see. The resolution is the number of pixels that are in the screen. So I think it's when you do 320 by 240, multiply it, and then depending on how many colors each dot can do, that's how they figure out resolution. But the industry standard generally is 320 by 240. So as you can see on the camera here, it's basically 320 this way, 240 this way, and that's what'll give you your number of pixels. So that's why when screens get larger, but the pixels stay the same, you don't get as good of an image. Whereas if you have a smaller screen, you don't need as good resolution generally, because the screen is smaller, and so the dots themselves are smaller, and you're still getting a good amount of detail. So again, most of the time, advertised resolution only deals with the screen. And so what you get is you get something like this, where you went out and you spent, that $3,000 on a really nice 50-inch. I don't even know. I used to care about TVs. I couldn't care less now. But you went out and you spent a couple $1,000s on a TV, but you still have that shitty, Spectrum cable signal coming in. Sorry if anyone works for Charter, or whatever the case may be. So you got a crappy signal coming in, or you got your DVD player hooked up with coax or RCA, and you're not even using HDMI. That's the equivalent of getting a high-end screen with a cheap sensor. And a lot of times that's what you're getting on that $1,500 to $2,000 camera, where it's advertised as 320 by 240 or whatever. But it's the sensor inside or your cable box that isn't really up to snuff for what you're doing. All right. So that's something to be careful of. And really, I mean, you can delve into it a little bit, but the bottom line, if you guys are looking at new cameras, do everything you can to try and do it, demo them in a live fire environment and really, see how they react there. So the camera shutter is what the camera does to adjust to different levels of temperature. And this will paint the picture for what we talk about in the next section, gain modes. So the camera shutter is something, and the next couple things we talk about are things that happen automatically. So there's no user input necessary, but it is something that happens across the board. So regardless, I'm using a picture of an MSA camera up here, but regardless of that, you're going to find this in any camera manufacturer that you get. So the camera has a shutter and that adjusts automatically. It's important to know because a lot of times this is a complaint with cameras, is that my camera freezes. And really, generally, if that's a complaint that you have, it may be that you have, again, a less expensive shutter on there. There's a few things that it could be. The shutter could be out of adjustment, and a camera may be trying to, activate the shutter too often. But to know that if your camera's freezing or if it's just the shutter, when it freezes or when the shutter activates, you'll get that green square in the left side of the camera. So that would be the indication that the camera's shutter is, readjusting or recalibrating. And what it does, or when it does this, it does it as soon as you turn the camera on in order to focus and make sure that you're in the correct gain mode. It does it when there's a large change in temperature. So if you went from a regular room and turned the camera into a room that was of high heat, the shutter would recalibrate. And then it will do it at regular intervals to ensure that the camera is properly calibrated for the scene that it's in. Okay, so think of the shutter, or think of the calibration as maybe something that it counts in centimeters, and then when it gets to 1,000 centimeters, am I doing my math right? When it gets to 1,000 centimeters, it changes to meters or whatever the case may be. Like it's almost like an auto scale where the camera automatically senses that it's in a different temperature range and scales. I'll find out later if I did my math right. So gain modes, this is probably the most important part. The colorization of gain modes and the gain modes themselves is probably the most important part of the cameras, because this can be where there is a ton of misconceptions in the industry of how your camera operates. So cameras, and this is 90% of cameras, there are a couple that operate a little bit differently, but most cameras operate in two gain modes. They have a high gain mode, high sensitivity, and this is lower temperatures. So this is your room temperature investigation. This is your small smoldering fire. Generally, this is up to about 300 or 400 degrees. Okay. Then you have your low gain mode, which is a lower sensitivity mode, and that is for higher temperatures. So as you can see here, we have a low temperature scene. This is just that wall that I showed you before. I have a very low heat source here, but for the most part, we're looking at a room temperature wall right here. Although we'll talk about why it's inaccurate. We're at about 77 degrees. So again, fairly room temperature, although on a day like today, 77 degrees sounds like flashover temperatures to me. But, this was in the summer, so we're at regular room temperatures. On this right side here, we've switched gain modes. We're in the low sensitivity, so that high gain or low gain mode with that high temperatures. You can see that we're, in this case, we're at 260 degrees, but we're actually a lot higher than that. And again, I'll explain that. And so the camera has automatically, when I aimed it at this fire here, the camera has automatically calibrated, that shutter calibrated, it automatically adjusted to the low gain mode and adjusted for the high temperatures. Okay. So what happens if we only had one gain mode? Well, if it was this gain mode and I moved it to the fire, I would get whiteout basically. I would get a big blob of white here because it was so bright and so hot that the camera could not adjust to that sudden rush of infrared energy. Now, I use the term whiteout because that used to be a common issue with cameras. It was, oh, I couldn't see anything. The camera whited out on me. And that's exactly what happened. The cameras just did not have the technology to adjust, whether it didn't have it at all or it happened way too slowly. The cameras never adjusted for these high temperature scenes, and we're not able to see those high temperature scenes. And so you basically just got a big blob of white, and that was it. You basically put the camera down and continued on. If I had a camera that only operated in this low sensitivity mode, the high temperature mode, if I tried to look at this in high temperature mode, there is no way, shape, or form I would see this kind of detail here. Because here we're talking about probably, a wall that's 77 degrees and one part of it that's maybe 85 degrees. I should actually measure that one day with a real infrared gun. But we're talking about such a small temperature difference here that a camera that's in that low sensitivity mode would never be able to see the difference. So what is a gain mode? Again, it's non-adjustable. The shutter causes it to change. And basically what's happening is, the best way to describe it, I'll come back to this screen, but you're going to get that green. And this triangle, this green triangle in the upper left corner, or if you have an older camera, an L on the left side of the screen, those are the only ways, those are the only surefire ways across different brands to know that you've changed gain mode. So when that triangle comes in the screen there, that means that you've hit those high temperatures. And the best way to describe what a gain mode is here is, think about 3 o'clock in the afternoon, you're inside your house, your pupils, they're nice and dilated. They're letting as much light in as possible. Let's say you turned your lights off, and they're letting as much light in as possible so you have as much detail that you can see as possible. Now it's 3 o'clock in the afternoon, it's bright outside, the sun's shining. So you go outside and immediately look up at the sky. What's going to happen? Well, immediately you're basically going to get whiteout conditions in your eyes, right? You're going to look in the area of the sun, and the sun's going to be so overpowering that you're going to not be able to see anything of what's going on in the sky. So what do? Well, what the camera does is it basically puts on a dark pair of sunglasses, and it says, okay, well, it's way too bright, so I'm going to put on these sunglasses, knowing that I'm going to lose a little bit of detail, because when we put on sunglasses, we don't have we don't get as much detail in, but you're still able to see, even though it's really bright out. That's basically what the camera is doing. It's saying, okay, well, I'm getting a ton of infrared energy, so I'm going to change gain modes. Even though I won't be able to see as much detail, I'll at least be able to give you a good picture in these really high heat conditions. And that's exactly what the camera is doing in order to give us a good, that's what it's basically doing when it changes gain modes. The other part with gain modes that I want to talk about is the bottom here. When do we change gain modes? So this is where we diverge among different manufacturers in the industry. So, we obviously, we've talked about why we change gain modes, but what are the exact parameters to change the gain modes is going to be different by every manufacturer. So for example, MSA changes when it's 34% of the screen is above a certain value. Argus changes when it's either a percentage of the screen is above a certain value, or if that center target, the center green section, is above a certain temperature. So the bottom line is, it's going to depend on your manufacturer. And we don't have time tonight to go through every single manufacturer, but some of the issues that I've heard of people having with whiteout on their camera in relatively lower heat conditions, I believe it's because they're only getting a part of the screen at high temperatures, but not that center target. And if the camera does not adjust gain modes, if just that center target has high heat, then that camera may not be shifting into the low sensitivity mode for the high temperatures, and that may be what's giving you your whiteout conditions. So we could delve into that more, but probably not tonight. I want to just so I know that might be a little confusing, but basically, sometimes I think what's happening is the camera's not adjusting gain modes, and that's maybe why you're getting whiteout conditions when it's not super hot in the environment. So the other thing to go along with gain modes is, what do colors mean? So the short answer is it depends, unfortunately, because even in the NFPA standard, there's no standard on what color has to mean in a camera. So the color is inserted based on how the camera is programmed. On some camera manufacturers, color is based on a temperature. On some manufacturers, color could be inserted as whatever the hottest item is in the screen, or the hottest image is in the screen, the hottest state of matter. On some, it's user adjustable. So Bullard has what's called the throttle control, where they can actually change where the color gets inserted into the camera. And then what we'll talk about in one of the next slides is some manufacturers will reset the color scale when the gain modes change, and some will keep it consistent. So this is probably the most important. If there's anything I would say tonight, the next two slides are probably the most important part if you're not super familiar with your camera. And so what I want to point out is, I don't know why I put these in this order, but on the right, we have a camera that is the way we turn it on. This is the high sensitivity mode. And on the right, we have a camera that's switched into the low sensitivity mode for high temperatures. Okay, so without looking at the color scale, without looking at the temperature readout, without looking at anything on the, other than icons on the camera, how do I know that the camera on the left is in a high temperature environment and the camera on the right is in a low temperature environment? Again, that green triangle is all I need to know, regardless of the manufacturer. That is NFPA standard, that if my camera switches to a high temperature environment, or my camera detects a high temperature environment, I am going to have that green triangle in the upper left-hand corner, okay? So what you want to look at with these two images next to each other, although they're in different areas of my house, want to look at the scale on the right side. If you see that regardless of whether we're in the high temperature environment or the low temperature environment, the scale on the right remains 0 to 2000, 0 to 2000, and you can see that color gets inserted at the same temperatures. So yellow starts around 700 degrees there or so, and you can see orange around orange to red around 1500. So you can see that the color scale on right and left is 100% identical, okay? And that's important because when we go to the next screen and we go to, this happens to be an MSA camera, and you can tell it's a last NFPA spec. There's your L. So that's the L that indicates we're in the high temperature mode. It's just not the current NFPA version. But what I want you to really look at here is our scale for the camera when we are in that high sensitivity mode is 0 to 300. And then our scale when we hit shift into that high heat mode is 0 to 1000. But more importantly, we have color here and we don't have color here. These pictures or these images are taken almost identical to each other in time. So has the environment changed at all? No, the only difference is that the camera's gain mode changed. However, the colorization changed drastically on the camera, right? I have color here and I have no color here. So that's a very important aspect of cameras to realize, is that sometimes the color scale in the high sensitivity mode is going to be 0 to 300 or 0 to 500. And then when the gain mode changes and it shifts into the low sensitivity, high temperature mode, your color scale is going to shift as well. So you cannot go with the, oh, well, if it's red, it means it's fire, or if it's red, it means it's the hottest thing, because your color scale can change as your camera's gain mode changes. So that's a very important aspect. And it's going to depend on your manufacturer of your camera, how that works. So I'm going to take a quick second. Are there any questions about that concept, the game mode changes? And obviously it's easier to show in person and with the cameras in front of you. But I wanted to do my best to show it via picture as well. All right, so there's no questions on that. What is standard with color is the order that it goes in. So you're going to have black as the coldest, dark shades of gray up to lighter shades of gray to white as you get hotter, and then yellow, shades of yellow, orange, and red as you get even hotter. So this is standard. It's just not standard where you put the color in. So you're never going to have a camera where yellow is hotter than red, or orange is hotter than red, or yellow is hotter than orange. The order of these colors are standard. What's not standard is where you put them in. So most cameras, it will be black, gray, shades of gray to white as just contrast of temperatures, meaning that white is not a specific temperature. It's just simply white is hotter than gray is hotter than black. And then where camera manufacturers diverge is where the color goes in. So again, some will be, say, yellow will be 100 degrees, and then orange will be 150 degrees, and then red will be 300 degrees in the high sensitivity mode. But then when it changes to the low gain mode, now suddenly yellow is 500 degrees, orange is 800 degrees, and red is 1200 degrees. Whereas some, as I said, will stay the same, and you'll have color as a specific temperature throughout the gain mode changes. So again, it's important to know what's standardized across the board and what is up to the manufacturer to determine. So we talked about contrast of temperatures being an important part of what we are seeing of how we're going to see an object. And the other important part is going to be of how we see things is going to be that it's relative temperatures. So in this case, we have a bottle of half and half that's been stored in a fridge for an extended period of time, because that's where we store half and half. And as you can see, if I take it out and I put it on the counter, the half and half shows up as black. In the same second, I put it in the fridge, and you can see that the bottom part here is about the same color as everything else around it. And then the next second, I put it in a freezer, and you can see that it's lighter. So did I take the half and half and give it and cool it down quickly and then bring it to fridge temperature and then put it in the freezer and heat it up? No, of course not. What I did was simply showing you that a camera is not going to always show one object the same. It's going to show the relative temperatures, and that's what's going to show you a specific object. And so obviously the most important example for that is when we conduct search and rescue, in a fire environment. We don't want to say, well, the person's always going to, we always play in the firehouse and hey, can you see me? And the person shows up as white. And that's just because generally we're in a room temperature environment. People are 98.6 degrees. So 98.6 degrees is generally 20 to 30 degrees hotter than what your ambient temperatures are. And so they're going to show up as the hottest item in the room. If I put that person in front of a fire, well, you damn well believe that 100 degrees is going to show up as more of a darker gray black object next to a fire that's burning at 800 degrees. Obviously, that's not something that we should probably do, because then we're, going to have some issues. But it's important to explain that people are not always going to show up the same as we see them in room temperature when we're looking, and playing around in the firehouse. So, you go back to your department. This is a very quick, easy example to be able to do that, is to show that. You can use a cup of coffee, so there's a lot of different things that you can use to show how a camera really just gives you an image based on contrast of temperatures, but also that black shades of gray to white is going to be based on relative temperatures and not a specific temperature. All right. Again, this is an example of colorization based on specific temperatures on the top. So that's why, here on the top left, we're getting color inserted because we've hit those specific temperatures on that scale to get color to be inserted. On here on the right, top right, we don't have color because we haven't hit those specific temperatures. So we're simply operating in grayscale, black, gray, white to the hottest. And then on the bottom two images, you can see that these are colorizations inserted based on contrast, or based on the hottest image in the room. So we're actually picking out specific points of the fire that are the hottest parts, because that part of the fire is hotter than this part of the fire. And then on the right here, we're picking out specific parts that are hotter than the rest of the image. So again, it would be incorrect to give someone a camera generally and say, here, go turn this on, and if you see color, do this. Generally, that's not a good thing. There are a couple of manufacturers you can do that with, but it's important to know where you can and can't give that, kind of direction to. All right, so moving right along. So obviously smells and bells, I'm gonna start skipping through a little bit now. We got through some of the big basic stuff. Obviously, when we get into smells and bells, we're gonna be operating in that high sensitivity mode because these are not high temperature environments generally. And as a rule of thumb, if I don't have my face piece on, we're probably not going to be shifting into that high temperature environment. But there's a lot of different, I'm not going to tell you guys anything you don't know about, smells and bells or going on all these odor investigations. Suffice to say, what I would say is I see a lot of departments that are still going out there. This is my tangent. Walking into houses for odor investigations with their, surgical masks or N95s on. Listen, if the people are concerned, then have them go isolate or leave the house for a minute. But we got to take those masks off to get a good idea of what the odor is, because as we know, there's a lot of different odors out there. There's odors of belts burning, odors of overheated outlets, electrical wiring, oil burners. And if we're breathing through an N95, we're really not, we're doing ourselves a disservice, and we're probably going to end up there longer than we have to be. So again, this is a low temperature environment where visibly with the naked eye, we have nothing going on. But with that thermal imaging camera and the infrared energy at the high sensitivity setting, again, no triangle in the upper left corner here, so we know that we're in that high sensitivity area. We can see that we're picking up a heat source here. Again, that heat source is not in color because we have that scale on the right, that 0 to 2000 degree scale, and we haven't hit those temperatures for color to be inserted yet. So again, the way I like to do investigations is, again, just start at the door and take a big, good scan of the room. If we try to walk up to a wall, you're going to end up with some of those early images that I showed you tonight of a featureless image. So take a nice big scan from as far away as you can to be able to see what's going on. And again, are we seeing through walls? Of course not. We're not seeing through the wall. We're simply seeing the infrared energy that the wall is putting off by touching the heat source there. So basically you have the heat source touching the wall. So it's conducting the heat to the wall. And then you have the wall putting out that infrared energy. And that's what we are picking up on the thermal imaging camera. So if we end up maybe in a confined area, or we end up in front of a wall where we kind of have that featureless image where we really can't see what's going on, if we can't back up, or we still cannot get a good image of what's going on, a good a contrast, then we can create our own contrast with our bare hand. So we got to take our glove off. We use our bare hand, and as I mentioned, and hopefully you guys all know, around about 98.6 degrees, right? So if I put my hand in front of my face and then look at it with the camera, and I have the wall that I'm trying to investigate behind me, just a contrast of temperatures. So if my hand's showing up as white, which is on the left side here, then my hand is warmer than what the wall is behind it. That would be fairly normal. I would expect that my hand would be the hottest item in the screen, just like we talked about, shining it among the classroom. On the right side here, I put my hand in front of a wall, but my hand is showing up as darker gray to black. So now, if my hand's 100 degrees, just as a roundabout number, my hand's showing up as colder than what the wall is, and the wall is more than 100 degrees. So that probably warrants some sort of further investigation. So someone asked, at what point do you lose accuracy? At what distance do you lose accuracy? And it's a great question, and it's a tough question to answer as a number. What I'll say is they say the cameras are most accurate at 3 feet, or that's where I should say not most accurate at 3 feet, but you shouldn't go less than 3 feet. So if you get closer than 3 feet, you're most likely not going to get an accurate readout, and you may start to get like a blurry image. So if you can get 3 feet from your object at least, that's ideal. Now, in terms of how far can you get, a lot of it's going to depend on how much energy the emitter is putting out. So, for example, if I have 100-foot length of a field or something like that, and I put something at the other end, a very low energy emitter, I'm going to be able to see that. How do I say this? The more energy something's putting out, the farther away I can be and still get a good image. I guess that's what I would say. So fire, I could probably be a few 100 feet away and get a good image out of it. If I had a really small, item that was maybe a passive emitter at this point, and I put that 100 feet away from me, I might not be able to see that. And so it's going to depend on how much energy it's putting out. And again, more importantly, it's going to depend on what the contrast and temperatures are around it. And so if I put something away from me that is, I don't have the picture here, but it's a picture of my dog in the woods in the middle of winter, and he sticks out like a sore thumb even a few 100 feet away. And most of the reason is because there's such a differentiation in temperatures. All right. Someone asked, is the terminology heat signature a term we should be using with thermal imaging cameras? I certainly think a heat signature, I don't think it's a bad term. I would then kind of diverge into, is it an active heat signature or a passive heat signature? If you were, it depends what you're looking at doing, I guess. You're certainly going to have a heat signature. If you have a heat signature, there's something that is hotter than everything else around it. Mike, that's a good question. Let me think about that for a little bit. I don't really have a problem with saying heat signature, but I think, again, it depends what you're looking for. If you're looking for a victim or fire or just, like a passive emitter. Let me think about that one. That's a good question. Kind of delve into that a little bit. We talked a little bit about this, so I'm going to skip through it. But we talked about kind of backing up and looking and trying to get as big of a image as we can in the camera. And then obviously clean gear and fresh noses is going to be important. We got to be able to do that. We got to clean our gear so that we're not smelling everything else going around. So there's a lot that we can see from the outside, especially depending on what the building is made out of. But I've had officers or chiefs that have told me that they were able to see fire running up the walls in balloon frame construction. Heat signatures. There I go. Heat signatures from like the Bilko door, because the Bilko door being made of metal. Here's an example. Obviously, the Bilko door being made of metal is going to transmit infrared energy better than a wall will. And so on a 360, that might give you an indication that you have a fire in the basement. So that the camera's a good thing to use on a 360. It's a good thing to use as you're walking up to the building. To go along with Bilko doors, where it really becomes handy would be a series of roll down gates where you have a lot of smoke pushing, but you're not sure exactly which store it's coming from. And so shining the camera, again, backing up and getting all of the gates in one view and being able to pick out the one metal gate that's hotter than the rest can definitely be, an important, a good hint. But again, you have to do that from farther back, because if you're up close, you're only going to get one gate in the picture. And so you're not going to get that relative temperature difference and the contrast in temperature. So you're not going to be able to pick out one gate that's hotter than the rest. All right. And this is just a homemade prop indicating fire spread. So this is kind of, again, showing you you can't really see much from looking at it. Sure, you can see some charring down there. But once you take the thermal imaging camera, you can see that I basically built a platform construction stud on one side, or wall on one side, and a balloon frame bay on the other side. Bay is the word I was looking for. That's the problem with doing this online is if I can't think of a word, I just sit here and act like an idiot for a minute. So, but you got a platform bay on one side and a balloon frame bay on the other side. And again, just a quick, a quick drill to show how the camera shows, different images and whatnot. And again, we're not seeing through walls. We're just seeing the infrared energy that the wall is putting out here. So that's a good example. And generally what we do in the practical portion is we'll start out with like a charcoal igniter in there, and that's what that emitter. Yeah. So Mike, I keep saying I keep wanting to say heat signature. So yeah, I think heat signature is a valid term that you can use to describe anything that's putting off heat. I would say that in my mind, it probably deals more with an active emitter. Um, but you might see it in any case. Yeah, so I don't think that's a bad term to use. So I put the charcoal igniter here. It's just an electric charcoal igniter on here. And again, that conducts the heat to the sheetrock drywall. And then I see the image on the outside from the infrared energy it's putting off. So very basic drill you guys could do, in your parking lot. So again, as I said, at the front door, there's a lot that you can do in order to see what's going on inside. Now, sometimes we're going to have fire blowing out of a window and it's going to make things a lot easier for us. Other times we're going to have to actually find the fire. And so I talked about the gain mode being one of the most important things for the night. I think this is the other really important thing for the night, is trying to have the ability to take a minute and point the camera directly up at the ceiling. And what you guys should be able to see is you should be able to see this infrared energy moving from right to left. If you guys scuba dive, anyone scuba dives, this kind of reminds me of scuba diving, under the water, seeing the bubbles move one way. But this is the best indication most of the time of the direction to go towards the fire, even in zero visibility conditions. This is just a repeat of the video as I talk. So just to explain that. But if you look directly overhead, you can see that infrared energy moving from right to left. And so I know as I enter this room, I need to go towards the right. Now, this is another example where we're kind of looking a little more ahead of us rather than directly overhead. And what I like to show here is that when you're not looking directly overhead, so right in this case, when you're kind of ahead, shining it ahead and not directly overhead, it's a little hard to see which direction the waves are moving. So you can see once you shine it up directly overhead, it's a lot easier to see which way it's moving. It's almost like being in the bleachers behind home plate. The batter hits the ball and you think it's going, over the center field bleachers, and it pops up to the catcher just because your depth perception's not there. Same thing with the camera. And that's why the best thing to do for direction of the heat moving is to point it up directly overhead, 100% directly overhead. All right. So here we didn't point it overhead, but you can see that you're getting very clear left to right movement. So this would be after I pointed overhead. So I come in this door, pointed up overhead. I see the waves moving towards me, and now I look straight ahead, up straight ahead, and I can see the heat waves moving left to right. So again, that's indicating that my main source of infrared energy is down here to the left. All right, so again, we want to look up, find the seams of the room. After looking up and seeing which way the infrared energy is moving, finding the seams of the room at the upper ends is going to give us a good idea of how large the room is. If we aim the camera low, we're generally not going to get a good idea of how large the room is because there's so many objects, furniture and whatnot, in the way and whatnot. So it's best to do it up and use the seams of the room. And then from there, what we can do is scan the lower part of the room so that we can determine objects in the way, couches, victims, things like that. Okay. So here we look up overhead, and then I think that's what this is. Yeah, this is just another example of looking up overhead and seeing that infrared energy moving. The one time to be careful about looking up and overhead would be the one time to be careful about looking up and overhead would be when we are in again, a low emissivity environment. So when we go back, if we have polished steel or something like that, or really cinder block, so again, because it's got that low emissivity, what can happen is that sometimes you'll actually get a reflection of that heat energy. And so you have to be careful when you do that, when you're in those environments, that you make sure that the heat is not just bouncing off of a wall. So the best way to do that, where we see it, is kind of projects and whatnot. So projects have that really shiny cinder block walls. And so we aim the camera up at the ceiling, and sometimes you'll see the energy moving, very distinctly in one direction. So you still have to look left and right to ensure that it's not moving against the wall and then bouncing off and coming back. So that's an important part as well. So turn your volume on. This is the most important part of the program. We don't want to use the camera as a GPS, right? Because when we use the camera as a GPS and we just go like this, camera only has about a 50-degree field of view. Our SCBA only has a 90-degree field of view. And so we're choking ourselves down. And we're going to trip over things. We're going to miss doors. Stairs are very complicated to see on a camera. It's actually very difficult to look at a set of stairs and see if they're going down or up. So if we use the thermal imaging camera as a So that's why we can't use this as a thermal imaging, as a GPS, right? That's probably what happened in Stanford, for all I know. So, but this is an example of looking at the seams. So that obviously this is a burn room, so there's nothing on the floor. But if we use the seams and scan the room, we'd be able to get an idea of how how large the room is. Okay. All right. So now we'll talk about hallways. Night, buddy. So we'll talk about hallways a little bit. And this goes back to where we were looking at with the pixels, where the 320 pixels along the top versus 240. This is where that kind of comes into play a little bit. When we turn that camera 90 degrees, we're going to get the taller view instead, vertically instead of horizontally. And so rather than try to explain that, here's a picture. So when I hold my camera, right side up like normal, this is the view I get on the right. All right. I get my view wider than tall. So where a hallway is fairly obviously narrow and tall, I'm getting a lot of wall here, which I really don't need. And so simply by taking the camera and turning it 90 degrees to the left or the right, it doesn't matter. It's not going to matter which way you turn it. If I turn that camera 90 degrees, now I'm getting my 320 vertically and my 240 horizontally. And you can see that I'm getting a lot better view of the hallway. I'm still getting the walls, but I'm also getting a lot more of what's going on at the ceiling level as well. And so if you find yourself in a hallway, this is a quick tip to be able to kind of get a better vertical view and not have as choked down of a horizontal view. All right, and then when we end our scan, we're gonna want to end it with the floor and check for any obstacles. In this case, we have a hose line. But again, a lot of these houses now with hoarding situations, there's so much to navigate. All right, so end that scan on the floor and see what kind of obstacles you have in the way. All right, so fire attack, again, not just finding the fire, but getting water onto the fire. The water's, going to be colder than the fire, obviously. So the water should look black. I like to allow the nozzle man to take a look. So if I see the fire, give the nozzle man a quick view, kind of show him what he's attacking. And it's just going to help you in the long run than having to try to yell at him once he opens up the line. And again, it's all about contrast. So in this case, we have a hot fire and we have a cold water stream. And so we're really going to be able to do a good job of aiming the hose line at the fire. So some of the overhaul searches. I missed that. All right. So a lot of times we're searching with 2 or 3 people. You know, depending on the department, sometimes it's two, sometimes it's an officer and two guys. But basically, the two ways that we teach to use a camera in a search would either be a camera-led search or a camera-directed search. And so, in a camera-led search, basically, I have the camera, my firefighter's with me. We want to navigate from point A to point B, and so me with the camera is going to lead the firefighter without the camera. Okay, this would be good in a larger environment where maybe we're using a search rope. This would be good in a larger house where maybe we have to navigate to a certain area. And again, the person with the camera is going to lead. If you're gonna, you just have to be careful that you're not going faster than the person without the camera, because again, they haven't seen a view, so you know, you want to make sure that you're not crawling away from them. In a camera directed search, this is where maybe the person with the camera is going to stay at the bedroom door or at the window. If you're performing VES, they'll stay with the camera and then send the searchers in to go do their search. And that person with the camera has a couple jobs. Number one, monitor for fire conditions. So if things are starting to get shitty, make sure that he calls them out. Number two, be a beacon for them so that if they get lost, obviously they can get back to their point of entry. And number three, make sure that they're not, you know, crawling into another area of the house without realizing it. You know, a lot of these rooms might have, you know, one door to the hallway, but then another door to a bathroom that shares with another bedroom. So that could certainly end up being an issue. So this would be an example of a camera directed search where the person with the camera is the red. And so they're staying at that doorway and scanning the room while the person's conducting the search without the camera. All right, so someone asked a really good question. While you're not using the camera as a GPS, if you're a crew of two, how often should you actually take the camera out and check it? And you know what I like to do is every time I get to a doorway, kind of rescan what I'm looking at. And so in this case, you know, this is a kind of blown down version, but if this was the front door right here, you know, I would be here, scan the area, and I would be able to get a basic layout of what this room was like. And so then I could, you know, say, okay, we're going to go to the right here and do a search. So we would crawl here, do our camera led search to this room. And then once we got here, I would take the camera out again, scan this room, and then send my searcher in to do the search in there. So, you know, a lot of it's going to be situational dependent, but for the most part, I'll take the camera out and look every time I get to, you know, a doorway or a different room, or if it's just been a few seconds. What the best way it was described to me was for a lot of the career guys that have shared bunk rooms. I don't know if that's anyone, but we have shared bunk rooms, and so it used to be before a cell phone. Every cell phone had a flashlight. It was you went in, turned the lights on in the bunk room quick, took a quick view of what was going on, said, all right, I'm going to that bunk, and then turned the lights off and shot to that bunk. And that's basically a kind of good example of what you're doing here. You want to take the camera, get a quick view of what's going on, and then put the camera down, go do your search until you get to the next point. So large area search is another whole part in itself, and this is something that we're going to include in our thermal imaging camera classes, more for working with search ropes rather than actually using the cameras. So I'm not really going to address large area searching too much tonight, but this is obviously a big part where you could use the camera as well, again, in a combination camera directed and camera led search combination. Okay. So some basics with search, we use the TIC to get a layout of the room. And obviously if we spot a victim, then we're going to be that much quicker getting to them. The number one rule, though, is that we're not using the camera to search. And so if I look into a bedroom and I don't see any victims, that does not mean that I don't go in and do a search there. We're only going to see line of sight with the camera. If someone falls behind the bed, if someone's, you know, unconscious behind a dresser, or however it's, you know, behind a door of how it's open, the camera's not going to see them. And so we can use the camera to pick out objects. We can use it to pick out people. But we can't use it as, all right, command primary search is negative. Okay, so if we see a bed, good, we can go beeline it to that bed, but we're not going to use the camera to conduct our search. So overhaul, again, this is another point like search where it can help us, but it should not be the end all be all. Overhaul should be conducted until we get down to clean wood. So we should not be saying, all right, I had a fire in this room. I have some charring above me, but I don't have a heat signature. So I'm not going to pull the ceilings. That's not what we're here for. But the camera can certainly look at a ceiling and say, you know what, I have a hot spot there. This area is showing hotter than that area. Let's start overhauling this area first. So that's definitely where the camera can play a part extremely well. So in this example where maybe we had a fire down here, in this area here on this wall, scanning the camera up above the ceiling here could certainly show a heat signature that may determine that we need to open that up quicker than normal. So we can kind of get a baseline of where we want to start opening up on the floor above. On the floor above, we can scan the baseboards here and maybe get an idea if we have a heat signature. This might be an example of what we see on the floor above with the heat signature coming up in the walls there. And so we can definitely use the camera to, get us going a little bit quicker. But the bottom line with overhaul is we need to use our common sense and we need to open up, okay? The camera should not be telling us not to open up. It should only be speeding us up where we should open up, if that makes sense. You got it, just like search, you got to go back to the basics, get down to clean wood, wash everything down. We want to limit our rekindles. All right, so some of the limitations of cameras. Masked objects is a big issue, specifically with search. And I see someone put a question up here. It's a little bit longer, so I'm just going to get to it in a little bit. So we have masked objects where someone or something, an active emitter, is underneath something else. And most obvious would be on someone underneath their covers. So they're putting out 100-degree heat, but the covers are doing what they're supposed to, which is keeping all of that heat in. And so it's basically a passive emitter covering an active emitter. And so a heavy blanket's a good example. And in this case, this could be, here we're talking about it and I'm aiming only at one thing, but this could be a very easy thing to miss if you scanned a room and not seeing that. So again, we don't have a huge differentiation in temperatures. We have a masked object underneath a heavy blanket. And so we still need to conduct our primary search as if we would without a camera, okay? But masking of objects is a major issue. The other in an overhaul or fire in the wall mode would be like a double sheetrock insulated wall. The insulation keeps it in, double sheetrock keeps it in. And so again, all of our senses have to come into play. If you smell something burning, just because you don't have a heat signature on the wall, if you've narrowed it down to something in there, you got to open up the wall. Thermal imaging camera cannot see through water. So for those water rescue calls, it's still an excellent tool to take to be able to see if there's a surface victim. But don't go in the boat and start scanning it. It's not side scan sonar. It's not going to see underneath. Okay. And it's not reliable to check for fire or structural integrity below you. And so this is an incident in Stamford a few months ago. You can actually see it was this was a first floor fire and this is the second floor, I believe. You can see the floor here has separated from the wall, and the carpet is actually what's holding it and keeping the floor from fully collapsing. And the officer with the camera, he knew that I'm still going to scan the floor, but he knew that the camera's not reliable for it, and he had no heat signature on it. And why is that? Well, if you're on the second floor and it was a first floor fire, you probably have insulation in the bays. You have a subfloor, maybe a floor or carpet. So you have a lot of materials that are insulating and masking that heat signature below you. And so again, don't take the camera what it's showing you for gospel. All right. So the other part we'll talk about real quick is direct temperature measurement. Their direct temperature measurement is going to be that temperature on the bottom right that corresponds to the center crosshairs. So I'll go back to that slide, but basically this measurement, this number corresponds to the center crosshairs there, okay? This has proven to be very unreliable in the new standard of cameras. it's actually not even on this. It's not even visible when you turn the cameras on. So you actually have to press a button in order to get to the get a direct temperature measurement. Just realize that the direct temperature measurement, it's an average of what's in that target. And we talked about emissivity. It's only going to see solid objects. It's not going to measure ambient temperatures. And remember, when we talk about flashover, what flashes over, it's not solid objects, it's gases. So it's not going to measure the temperature of those gases. It's going to measure solid objects, which don't flash over in the first place. It's only an average of what's in the crosshairs. And then most importantly, emissivity. So if I put, and I should probably do this as another example, this is a piece of wood that I left here. It's 111 degrees, but the ambient temperature was well over 200 degrees. If I had put then maybe a thing of steel, a thing of silver, you know, and a thing of ice here or something like that. Ice probably not a good example, but you know, if I put a variety of different pieces that had a variety of different emissivity values here, I probably would get different temperatures for all of them. And so again, it's very important that we don't use that temperature measurement to make any decisions. There are cases in this country where that temperature measurement was used directly to make decisions and caused line of duty deaths. So that number should not be used for any sort of decision making on the fire ground. All these graphs here are just an example of ambient temperatures versus thermal imaging. So you've got the red line is thermal imaging camera temperatures, and all of the other lines are ambient air temperatures. And so you can just see that it's not a reliable number or a reliable way to make decisions inside of fires. Okay. And again, this is just an example in a live burn. Just watch the temperature, how much it fluctuates just by moving the crosshairs on the fire and off the fire. I'm not moving in a room. I'm not putting water on the fire. I'm not doing anything to this fire other than, well, now I'm putting water on it, but I'm not doing anything to the fire up to that point other than moving the center of the crosshairs of the camera on or off the fire. And we go anywhere from 300 degrees, 260 degrees up to over 1,000 degrees. So I would not want to make my decision making based on that. And again, here's just my real world example, 90 degrees. And then you see the ambient temperature anywhere from 60 to 270 degrees. So you got a wide variety there. All right, this is the case studies I was talking about for direct temperature measurement. But again, we're kind of getting, I don't want to spend the whole night on this. So poor visibility with the camera. Again, the camera between whatever your heat source is and the camera itself is going to go through, you know, the infrared energy is going to go through the carbon particles, but we're still relying on regular vision to go from the screen of the camera to our eyes. And so if we have a very heavy smoke condition and we're holding the camera far away from us, then that's not going to work too well to be able to get a viewable image. You know, you'll have a viewable image on the camera, but we won't be able to see it. And so a couple of the ways to combat that: number one, we want to hold the camera as close to our face piece as we need to. And number two, we want to make sure that we're wiping all of the big three: the screen, so the screen of the camera itself, the germanium lens, which is this front part here, and then our face piece. We're going to have condensation buildup most likely. And so we're going to need to wipe these areas as much as possible as we go through it. We talked about field of view. We got a narrow field of view here. And so we need to make sure that we're not using the camera as a GPS. And we want to make sure that we are kind of overly, scanning. So we don't just want to kind of look left and look right. We want to make sure we're really moving the camera left and right to be able to see the entire part of the room. Reflections have always been there. That's not new. This is standing in front of a regular window where I can see through it no problem with my eyes, but with infrared energy, it gets reflected off of it. This is not new. What is new in the last year are the amount of these, devices or materials that are being put up around all of these stores now. because of COVID, we have all sorts of different thickness Lexans, plastics, clear glass, whatever the case may be. And these could be a real hindrance if we try to go into a store or a environment and use the thermal imaging camera. These are all going to give us big time reflections. So it's definitely something to keep in mind, that you're not going to necessarily get that good contrast temperature scan that you would be used to. Talked about that, so I'll skip through that. All right, so let me read this. Let me read this question quick. All right. So I'll just read the question. I'm obviously not going to say who it's from, but I saw a post recently that said a tick is just a tick, right? Did you know that 41% of the U.S. Fire Service doesn't know the difference between the two main fire service thermal imaging cameras? It says know the difference and use them in the proper context for maximum effectiveness. It also states don't use situational awareness ticks for fire attack and search. There was a video posted along with it, but I didn't get a chance to. All right, so in the last few years, I'll take the screen out. In the last few years, there has definitely been an insurgence on what they call situational awareness thermal imaging cameras, and what they are is they're cheap pieces of shit. I mean, they work on the outside fine, but they're not going to work in high heat, high temperature environments for a few reasons. Number one, they generally, and they're number one with saying, oh, we have high resolution, this a 320 pixel, whatever. But the sensors are cheap. It's generally not, they're definitely not NFPA rated, so they don't go through some of the things that we'll talk about in a minute. The biggest issue with them is that they're going to have a very big shutter lag generally, and they're not going to have the detail that you're going to need to be able to see higher temperature environments. And so I've used them on the outside, and we had mixed results with them. We had a couple guys that had them at work, and they brought them, up to the roof. They're really small, they're really light, they're really easy to use, and so they didn't really weigh you down as much. And they weren't bad for navigating on a smoke-filled roof, maybe finding, where to start your cut, walking around the outside of the structure, maybe to pick out a heat signature. They're not bad for that because you're not getting it into a high heat environment where it needs to be able to quickly change between the high gain modes and the low gain modes. They're not made for interior structural firefighting. And again, just like anything, that's where the big issues lie. It's the same thing as like someone buying a Honda Civic and driving it on a day like today. There's nothing wrong with a Honda Civic, but it's not made to go out in 6-8 inches of snow. And it's the same thing here. And again, you get, marketing is king these days. And so you get, and so is price. And so that's where you kind of get into that issue with departments buying them as frontline pieces of equipment. But if you're going to use them in the correct way, which is outside, and I don't even know what a situational awareness thermal imaging camera is. That's not like a definition I can look up. I would not ever use it while I'm on air inside of a fire. But if you want to use it on the outside or for an investigation or something, have at it. But just know what you're getting. Basically, if it fails, you don't want to be, oh shit. And if you're inside of a fire and your camera fails, which rightfully so, you should be prepared for it to fail. You don't want to be, oh shit. So I don't know if that answers your question. If it doesn't, just you can follow up. I mean, we could spend a whole night talking about them. I don't have one here to show you, but I certainly think that overall, as long as you're not using it for interior structural firefighting, listen, I still think you're better off with a regular camera, even on the outside, because it's going to give you a better detail, better resolution with the sensor, and a much better, range of temperatures. But if you are going to end up with a situational awareness camera, just don't take it inside of a structure fire. That's all. And yes, I'm not surprised that 41% of the fire service does not know the difference, just because this isn't a topic. I don't even think they really address thermal cameras in Fire 1. So, there are a lot of people stop at Fire 1. So again, we're going to touch on the NFPA standard, and then I'll go through the Argus camera, quick sales pitch, if you will. So the NFPA standards, it's 1801. The minimum is 320. So there is a minimum pixel standard for the screen, and that's 320 by 240, which is 76,800. And again, that's because you don't just multiply it, but you also have the number of colors that each pixel can show. So a couple of things that are standard on the NFPA standard is the power button must be green. So that's important. So when you guys take a camera from anyone else, if it's got a green button, that's the power button. A single press of the power button is going to turn it on. And then if the camera's on and it's in some weird mode, if you just press the green button for 1 second, that will revert back to the standard thermal imaging basic mode. And if you read the standard, what it'll say is that when you turn the camera on, it needs to start off in the thermal imaging basic mode, and it must have the grayscale image with white hot, a power source indicator, internal electronic overheat indicator, an on indicator. So a lot of stuff that we're not really that doesn't really matter to you. The camera will not display the new spot temperature, like I said. So when you turn the camera on and it's a new 2021 NFPA camera, the spot temperature, that number in the bottom right, will not be displayed. And then when color is used, it must go in the order yellow, orange, red. We mentioned that before, but again, it does not dictate how color is used. So of all the things it talks about, color, how the color is used is not one of them. So this is an infographic a graphic, if you will, of what the NFPA version of a camera is. So the left side is going to be the additional information area. If you're recording, this is where your icon would be. If you're in the low gain mode, this is where your icon is going to be. If you're in any alternate mode other than the camera basic, this is where it's going to be. The center section is for the battery indicator. This triangle is a red triangle on the top. This is an overheat indicator if the camera actually overheats. Guys, don't worry about your camera overheating. The only time I've beaten the crap out of my demo cameras, I've had them in flashover simulators and everything. The only time it's ever overheated was when I used it in the flashover simulator as like a surveillance camera, if you will, and I had it in there for about 2 hours straight. That's the only time I've ever seen that icon actually come up. So don't be afraid to take your NFPA cameras into a flashover can. I bring mine in every time. I wouldn't put it first in line, but by all means, get it in the back, get guys able to use it. The center is your crosshair indicator for where the temperature measurement is. And then the right side is going to be that graph that's going to indicate where color meets specific temperatures. And then a sliding green scale on the inside here that will show what your direct temperature measurement, where that falls in line with your color scale. Okay. So again, these are all things that if you buy an NFPA compliant camera, these are all things that are going to be standard across the board, regardless of what manufacturer you go with. Again, that's where that red indicator is. That's the only time I've ever seen that happen. So some of the different tests, this kind of goes into why, and trust me, I promise we'll go through this quick, but this is going to talk about why the NFPA cameras are, we know what we're getting quality-wise with them. So they have a spatial image test, a vibration test, impact acceleration resistant test, corrosion test, a surface abrasion test, and heat resistant test. All right, flame test, labels are tested, temperature range test, field of view test, durability test. So there's a lot of, let's go back to a couple of those. There's a lot of different things that these cameras get tested on. And one of the important things to remember or to explain is that what will happen is they'll test the camera in a regular environment, and then they'll put it through these tests. So say they'll put it through the vibration test of 3 hours, and then they'll retest it. In the impact acceleration test, they'll test it, they'll drop it 8 times to concrete, and then they'll retest it. And so it's getting a lot of different tests that really beat the shit out of it. No, that's a great question. Not all cameras on the market are NFPA rated. So there are, first of all of the situational awareness cameras that we talk about are not NFPA rated. When you get into certain, so like Bullard will have some NFPA rated, some non-NFPA. Scott has some NFPA, some non-NFPA. Avon is one of the few that does all NFPA. So it's going to depend on the manufacturer. There are also some that will have the same camera, and you can get it non-NFPA or NFPA. The only difference being the price. And then you'll see some things that'll say like built to the NFPA standard. And basically what that means is they build the camera to meet the NFPA standard, but they don't spend the money to get the camera tested to the NFPA standard. It's very expensive to get a camera tested. You have to, aside from paying the testing fee, I think you have to send them 30 or 35 cameras or something like that you'll never get back again. So it is expensive to test cameras to the NFPA standard, especially if you run into an issue. So, all right, so that's about it for the PowerPoint. Does anyone, I'm going to stop the share and I'm going to ask if there's anyone with any questions. I see that there's one question up there, so I'll address that in a minute. But is there anyone else that has any questions? No? Okay. So just give me a minute. I'm going to eliminate my background, my cool flash fire background, so that I can share a little bit of what's going on. All right. All right, so someone is all right, so someone's asking now that you mentioned it, what manufacturer would you say is more of a situational awareness camera? So that's a good question. We're actually talking about we're saying situational awareness camera. So what is a situational awareness camera? So let me pull up a couple of examples of what I would consider or what it would be considered. So the biggest one is probably this one, the TIC thermal imaging camera. This is probably the most well-known situational awareness thermal imaging camera. It's probably smaller than a cell phone. It's about cell phone size. It's a rechargeable battery. Again, it says it can go to 1,000 degrees, but what you're going to find is that it lags. It has a very choppy image, a very low frame rate. That was one thing I didn't mention in the NFPA part that I probably should have, is that there's a minimum frame rate. So I think it's 30 frames per second. And so this is, I believe, has a much lower frame rate than that. The sensor on it is much cheaper, so it takes a long time to adjust between gain modes. And so that's what you're going to get with a situational awareness camera. FLIR is you mentioned FLIR, you have FLIR on one of your rigs. FLIR is a very interesting line. And without getting too much into it, this is the K2. This is like that $1,000 camera. This to me is still a situational awareness camera. However, FLIR does make nicer cameras that are NFPA compliant. And so again, it's like saying I have a Chevy. Well, you could have I'm not going to offend anyone with what you have, but you could have a cheap Chevy or you could have an expensive Chevy. And so same stuff here with cameras. You could have a cheap FLIR that's garbage, or you could have a K65 that is, fully NFPA compliant. And while it's not my favorite camera, it's a very good functional camera. What's interesting though, FLIR got into the thermal imaging camera market because they make the sensors for most manufacturers out there. So I don't know specifically which ones, but they do make the sensors that, say, MSA puts in on their thermal imaging camera. MSA does not make their own sensors. And so FLIR basically said, well, we're making all these sensors for other companies. Why don't we get in the game ourselves? That's how FLIR got into the game. I believe they just got purchased also. But like Avon makes their own sensors. So you're not buying, you're actually getting their own sensor in there. So if there are no other questions, I'll just say flat out, I sell the Avon. So, you could say I'm semi-biased to it, but I try to be, when I do demos or do training, I take it very seriously. So I think I'm pretty objective, and frankly, I use the MSA camera at work and I like it a lot. And there are some things I like it better than the Argus, and I'm happy to say that. So I think there's some very good cameras out there, not just Avon. However, I have had very good luck with the Avon camera. And so the entire Avon line, ranging from about $4,000 up to $6,500, is all NFPA compliant. So all the cameras, regardless of which one you get, is NFPA compliant. They all come complete with the truck charger, 2 batteries. So it comes with 2 batteries. It comes with the truck charger, which is right here actually. So this is the truck charger. It comes with that. It comes with all the mounting hardware. It comes with all the cables and cords and power cords that you need. It comes with a retractable lanyard that goes on either side here, so you can put it on one side or the other. So we've had very good luck with it. It also, the germanium lens on the front here is user replaceable. So if you ever scratch that or dent it or whatever, break it, that's replaceable in the field. So it does not need to go back to the manufacturer for that. The warranty on it is anywhere from 3 to 5 years on the bumper to bumper itself, and then 10 years on the camera, on the sensor. So basically lifetime. When you turn the camera on, it's a under 5-second startup time. So when you look at some other manufacturers, it has up to 20 seconds to start up. This has an under 5-second startup time. And again, what I like about Argus, Avon, it used to be Argus and they were bought out a few years ago, is that scale on the right side, 0 to 2000 degrees, does not change when the gain mode changes. And so why that's important is because you can teach this camera if you turn the camera on and you see color, you know you're at flashover temperatures or you're at least high heat temperatures, regardless of looking for that green triangle in the upper left corner, because that color scale does not change. And so you're only going to get color up at that 500-600 degree range. You're not going to have that scale change when you hit the higher temperatures. So that's a nice feature of it. More features than you can imagine. So you got laser pointer, compass, a variety of different color modes, picture and video taking capability. Like I said, 10-year warranty on the sensor. So really a lot going on with this camera. Some of the feature, and then you also have hot spot, cold spot tracking. So you can use that as well. So and as you can see, it's got 3 buttons, the power button being the on off. So that really, you only have one feature, but the other 2 buttons you can program to do whatever features you want. And so basically you have up to 4 features that you can work with on the camera. So a lot of different, it's kind of hard to show on the computer, so I'm not going to go through all of them, but you have a search mode, an overhaul mode, missing persons mode. And listen, my feeling with, features on cameras is that if I'm on air, I'm not pressing buttons. So, a lot of the features that I talk about are ones that I would use as long as I'm not on air, because if I'm on air, I don't really want to be dicking around with, all right, am I looking for the search mode or the overhaul mode or whatnot? But the search overhaul mode is very good if you're looking for those burnt out ballasts, or you got the fire knocked down and you're trying to find hot spots. What it does is it takes away that numerical scale on the right and simply colorizes whatever is the hottest item in the screen. It'll colorize it red so that you can say, all right, well, out of this room that was on fire, what's the hottest part so I can target my overhauling there? Or if I'm remote from the fire, it's not a high heat environment, you could hit that search mode, and then a person that's 100 degrees would generally show up as color because they're the hottest item in that room. So that's the Argus line. If you guys are interested in that, we have a ton of departments that use them throughout the state. We've probably sold 2 to 250 cameras or so, everything from Hartford, Trumbull, Stevenson, Monroe, Greenwich. So a lot of departments in the area have used that. And again, with any of the classes that we do that involve the live fire, we'll have demos there for you as well. So that brings us to 8:30. That's about how long I was looking for tonight to go. Again, I brought you through kind of a sped up version of the thermal imaging camera program. I hopefully gave you a little bit of information, maybe dispelled some myths, maybe created some questions, in which case feel free to reach out to me. I put a link in the chat box so you can, just leave a quick evaluation on what you thought of the evening. Anything else you'd like to see me cover in the future. March 1st, so some announcements. March 1st, we're going to do another one of these based on VES in the suburban environment. And so that's going to wrap up our winter series, if you will. And that's going to be all about VES. And so we're not going to talk about going off of fire escapes. We're not going to talk about, heavy duty multiple dwellings. We're going to talk about the suburban environment, the rural environment. what a lot of departments have around here. And that's going to kick off hopefully some VES classes coming this spring, summer, fall, with the new mobile container we have, where we're really going to focus a lot on VES and whatnot. And then no, it's VES, it's not VEIS. We'll talk about that March 1st as well. So that's going to be March 1st. And then I also have a few open enrollments coming up. I probably should have brought up the screen, but see if I can pull them up quick. We got a few open enrollments coming up. This one is going to be in Terryville. I'll move this over here. So this is going to be the fire behavior class that we're doing. And that'll be, I'm sharing the screen. Hold on. So that's going to be in Terryville on April 1st. So we're going to do April 1st classroom like this, either online or in person. And then April 3rd will be, in person Burns AM or PM. And then March 21st, if you're a training officer and you want to come, we will have a March 21st. If you're a training officer in Beacon Falls, we'll be doing like a modified version of our fire behavior class for training officers, kind of like this, where we skim through it and then send you through one burn just so you can get a good idea of it. And then Terryville, the 1st and 3rd, and then West Reading on Saturday, May 1st, we'll be doing fire behavior as well. And then hopefully following up with some open enrollment VES stuff later as well. So that's what's happening in our world. Again, that's pretty much what I have for you. So if you don't mind doing the survey, that'd be awesome. And hopefully we will see everyone out there again soon. So any questions, let me know. You know how to reach me. Thank you all for joining me, and have a good rest of your evening.